Today I'll talk about limiting and excess reactants and fractional conversion and extent of reaction. So before that we must know what is chemical reaction stoichiometry. First we need to understand the definition of chemical reaction stoichiometry. So chemical reaction stoichiometry is the study of the quantitative relationship between reactants and products in a chemical reaction. So it involves balancing chemical equation and understanding the mole ratios of reactants and products. Stoichiometry allows chemists to determine the amounts of reactants needed and the products formed in a reaction. Let's take one example and try to understand chemical reaction stoichiometry. Now here one example is given, that is combustion of methane. First so here that methane is bound with oxygen and that will produce carbon dioxide and water. So first when we get that chemical equation, so first we have to balance that equation. So here methane plus 2 oxygen, that will produce one that carbon dioxide and 2 H2O. So from this reaction stoichiometry, from this equation, so we will get lot of information like here. So how much oxygen required for the combustion? So here mole ratio is methane is to oxygen, that is 1:2. So if you have for example 2 moles of methane, so you need 4 moles of oxygen for the complete combustion. So we can get from this chemical stoichiometric equation. Now how much moles of water produced? That we can again get from this equation. So mole ratio oxygen is to water, so that is 2:2. So if you have 5 moles of oxygen, so you would produce 5 moles of water. Now how much amount of carbon dioxide formed from 10 grams of methane? So for that, so we need to convert mass of methane to moles and use stoichiometry and then convert moles to gram. So from this reaction stoichiometry we will get this information. Now next is stoichiometric coefficient in chemical reaction. So that is also very important. So what are the definition? What is the definition? In chemical reaction, coefficient are the numerical values that appear before the chemical formulas in a balanced chemical equations. So they represent the mole ratio of the reactants and products. So here the numerical values that appears before the chemical formulas. So here coefficient play a crucial role in stoichiometry, allowing us to quantify the relationship between amounts of substance involved in a chemical reaction. The coefficient in balance equation indicate the number of moles of each reactant and product participating in the reaction. So now here again I am taking same example. Now again that is the balance chemical equation, that is methane plus 2 oxygen, that will produce carbon dioxide and 2 water. Now interpreting coefficient. So now the coefficient 1, so here coefficient 1 in front of CH4 means 1 mole of the methane reacts. The coefficient 2 in front of oxygen means 2 moles of oxygen reacts. The coefficient 1 in front of carbon dioxide means 1 mole of carbon dioxide is produced. The coefficient 2 in front of water means 2 moles of water are produced. So that in each chemical formula the number comes before the formula, so that is nothing but stoichiometric coefficient. Now mole ratio, the ratio of moles of methane to moles of oxygen is 1:2. So based on the coefficient, means based on the coefficient we can get the ratio, and the ratio helps determine the amount of oxygen needed for complete combustion. So now we know chemical reaction equation and chemical stoichiometry, chemical stoichiometric coefficient in chemical reaction. So next is limiting and excess reactant, that is very important. So what are the definition of limiting or excess reactant? In chemical reaction, the limiting reactant is the substance that is completely consumed, determining the maximum amount of the product formed. In the excess reactant is the substance present in excess, not completely used up in the reaction. So which is consumed fast, that is limiting reactants, and which is in excess, the reactant is called excess reactant. So what are the key takeaways? Identifying the limiting reactants involve comparing the actual mole ratio of the reactants given in the problem with the stoichiometric ratios based on the balanced chemical reaction. If the given ratio is less than stoichiometric ratio for a particular reactant, that reactant is the limiting reactant. and the excess reactant is one not completely consumed in the reaction, and any remaining amount is determined after the limiting reactant is identified. So I'll take the one example and I'll try to understand all this statement. Now here, formation of water. So balanced chemical equation is 2H2 plus oxygen, that is 2H2O. So this is the balance chemical equation. Now suppose in the feed, suppose 4 moles of hydrogen is there, or reactor, suppose in the reactor 4 moles H2 and 3 moles oxygen is there. Now how much amount water will produced? So from here first we have to identify which one is limiting reactant and which one is the excess reactant. So for that first stoichiometric calculation. So compare the given ratio of moles of hydrogen to the moles of oxygen with the stoichiometric ratio from the balance equation. So from the balance equation, hydrogen is to oxygen ratio is 2:1, but in that reactor or reactants amount, so if you take the ratio, so that is 4:3. So given ratio 4:3 is less than the stoichiometric ratio, so indicating H2 is the limiting reactant. If that ratio is less than stoichiometric ratio, so that will indicate H is limiting reactant. So now product formation. So now from this, if we know the limiting reactant, so that is 4 mole of H2. So that is H2 is a limiting reactant. So from that we can easily calculate how much product will form. So calculate the amount of water formed based on the limiting reactant, and determine, also we can determine the excess amount of the other reactant, in this case oxygen. We can, if we understand if we find out that limiting reactant, so we can do the calculation. Now next is fractional excess of a reactant. Another definition, fractional excess of a reactant. So definition, the fractional excess of a reactant is the ratio of excess amount of that reactant to the amount of the limiting reactant consumed in a chemical reaction. So from this fractional excess reactant, so it provides information about how much of excess reactant remains unreacted relative to the limiting reactant. And the calculation involves determining the excess amount of the reactant and expressing it is a fraction of the amount of the limiting reactant consumed. Now, so here we can get some information of limiting reactant, excess reactant, fractional conversion, and extent of the reaction. So reactant that would be eliminated first if a reaction produced to the completion is called limiting reactant, that we already know. Other reactant are termed as a excess reactant. A reactant is a limiting if it present in a less than its stoichiometric proportion related to every other reactant. If all reactant are present in stoichiometric proportion, then no reactant is limiting, or they all are depending on how you choose to look at it. Okay, suppose Na feed is the number of moles of an excess reactant. So A present in the feed to a reactor. So Na stoichiometry is the stoichiometric requirement of A, or the amount needed to react completely with the limiting reactant. So Na feed minus Na stoichiometric is the amount by which A in the feed exceed the amount needed to react completely if the reaction goes to completion. So this is the excess amount of that reactant. So now what will be the fractional excess? So Na feed minus Na stoichiometry by Na stoichiometry. Now here I am taking one example and try to understand all these things. So here consider example hydrogenation of acetylene to form ethane. So here acetylene plus hydrogen, so that will form ethane. Suppose 20 kilomole per hour of acetylene and 50 kilomole per hour of hydrogen are fed to a reactor. So in the reactor or input 20 kilomole per hour acetylene and 50 kilomole per hour hydrogen. So now here from this is the balance equation. So from in this balance equation that stoichiometry is 2:1, means hydrogen to acetylene, that is 2:1. So hydrogen by C2H2 that is 2:1. Now, so here, so given 20 kilomole per hour acetylene, 50 kilomole per hour of hydrogen, so stoichiometric ratio H2 to C2H2, that is 2:1. Now ratio of, so from this stoichiometry, that is H2 by C2H2, that is 2/1, 2/1, 2/1. But in the feed H2 C2 H2, so that is H2 is 50 and C2H2 is 20, so that is 2.51. so now here, so from this ratio identify the limiting reactant. So here, that here hydrogen amount is this ratio is higher, so ethylene is the limiting reactant. So stoichiometric ratio is 2:1 and given ratio is 2.5:1. Since actual ratio is greater than the stoichiometric, so C2H2 is the limiting reactant. From this ratio, so you can see that hydrogen is excess amount, so C2H2 is the less amount, so that is the limiting reactant. So after getting that limiting reactant, so we can easily calculate what will be the fractional excess. So fractional excess, that is NC2H2, so that is not correct. So this is H2 feed stoichiometric and then that H2 stoichiometric, because we are calculate the excess, so H2 is the excess amount, so you will have to do that. So amount of H2 consumed, so excess amount of H2 by amount of H2 consumed. So here, so how much excess amount of H2 is there, so amount of H2 consumed, because 20 kilomole acetylene is the limiting reactant, so for 20 mole react with how much, 40 moles of hydrogen. So if feed is 50 and stoichiometric requirement is 40 and amount of H2 consumed 40, so fractional excess is 0.25. Now fractional conversion in chemical reaction. Now here fractional excess and then fractional conversion. In a chemical reaction with complete conversion, fractional conversion, that is F of a reactant, is the ratio of moles reacted to mole speed. So F is moles reacted, mole speed, and the fraction unreacted is accordingly 1 minus F. So from that, chemical reaction may not proceed instantaneously and the reacted effluent may still contain some unreacted material. In such case, a separation process is often employed to remove the unconverted reactant from the product. The separated reactant is then recycled to the reactant inlet to enhance the overall conversion. So these are the statement. Now here, how do you calculate fractional conversion? So for first, case number 1, suppose 100 moles of reactant feed and 90 moles of reacted. So fractional conversion will be 90 by 100, so 0.90, and fraction unreacted, so 1 minus 0.90, so that is 0.10. Then case number 2, suppose 20 mole per minute of a reactant feed and 80% conversion, suppose fractional conversion is 80%, so that is F is equal to 0.80. So moles reacted, so that will be 20 into 0.80, so 16 mole per minute. So mole unreacted, so that is 20 into 1 minus 0.80, 4 mole per minute. So from that we can, if fractional conversion is given, so we can find out mole reacted and moles unreacted, or if that how much reactant is given and how much reacted, so we can easily calculate what will be the fractional conversion. Next, extent of reaction in chemical reaction. So that is very important. What is extent of reaction in a chemical reaction? So definition: the extent of reaction, zeta, is a measure of how far a chemical reaction has proceed from its initial state to some later point. So that is very important. Okay, so from initial state to some later point. It is used to keep track molar quantities or flow rates of a reactants and product in feed and outlet stream. Suppose in the definition, so Ni minus Ni0 by stoichiometric coefficient. Now Ni is the moles of species I at the some later time, and Ni0 is the initial mole of species I, and nu I, that is the stoichiometric coefficient of the species I, negative for the reactants and positive for the product. So you have to remember this. So this is the formula. Zeta is Ni by Ni0 by nu I. So in Ni is the moles of species I at some later time, Ni0 is the initial moles of species I, and nu I is the stoichiometric coefficient of the species I, negative for the reactant and positive for the product. And zeta is dimensionless and start at 0 when the reaction commences. For a given reaction, zeta has the same value for all species. Now here one example. So A plus 2B, that is equal to C. So now here we also can take that acetylene hydrogenation reaction. So A plus 2B minus that is going to C. Now here nu A is 1. So stoichiometric coefficient that A is 1, stoichiometric coefficient B is 2, and stoichiometric coefficient C is 1. Okay, so definition of zeta. So for that, zeta is equal to Na minus Na10 by stoichiometric coefficient on particular component. So Na minus Na0 by 1. Okay, Nb minus Nb0 by 2, Nc minus Nc0 by 1. So these are the stoichiometric coefficient. So zeta start at 0, increase the reaction posit and has the same value for all species. Okay, so zeta has same value for all component. Now same thing. Okay, now here I am taking one example, ammonia formation reaction. So N2 plus 3H2, that will produce 2 moles of ammonia. So feed to continuous reactor. So in that feed, so nitrogen initial 0 here, initial, so 100 mole, NH2, not H2, NH2O, O means 0, so hydrogen is 300 moles, and argon is given 1 mole, that is inert gas. So that is no reaction will means argon will not take part in the reaction. So now outflow rate, so we can take that in any time that here. So we told that zeta, extent of reaction, means how far the chemical reaction has proceeded from initial state to some other later point, right? So now Nn2 will be 100 mole minus zeta, NH2 will be 300 mole minus 3 zeta, and NH3 is 2 zeta, N argon 1 mole per second. So how I will get this? Okay, so we know this zeta is N of hydrogen initial minus N of H2 by 3. Okay, so zeta is N H2 minus N of H hydrogen initial, okay, initial by new stoichiometric coefficient. Now reactant, this is minus, so it will be from here to here. So this will come first, NH2, that initial minus NH2 later by 3. 3 is the stoichiometric coefficient. So from that we'll get that N of similarly here from N of H2, moles of H2 is equal to NH2 initial minus 3 zeta. So N of N2 100 moles per second minus zeta, N of NH3 is equal to 2 zeta. So now here I am taking one example and try to calculate extents of reaction. Suppose the feed to a continuous reactor consists 100 mole per second of nitrogen and 300 mole per hydrogen and 1 mole argon. So that same example we took. Okay, so now given N of hydrogen in at 0 time, so that is 300 mole per second, Now here fractional conversion of hydrogen is given, so that is given 0.60. So now calculate at particular time what will be the NH2. NH2 will be 300 into 1 minus 0.60, so 120 mole per second. So from that we can easily calculate extent of reaction. So zeta 300 minus 120 by 3, that is 60 mole per second. So now from here we can easily calculate what will be the other component. So now we know 100 minus zeta and N of ammonia to zeta, so that we can calculate. So for 100 minus 60, 40 moles, 2 into 60, so 120 moles. So in particular time that N of NH2, so that is 120 mole,